Welcome to my channel. So in this particular video I'm going to discuss about the classic vanishing gradient problem. In the next video I'll discuss about exploding gradient problem. So let's start with the video. So this is in that, but as you can see in the in this particular image that I have taken two layer neural architecture. So this is nothing but all the input layers, and here actually I have taken hidden layer. This is the hidden layer and this is the output layer, and this is nothing but the y predicted, and which is the output of the particular neural network architecture. And this particular output actually we are passing through the loss function, where actually we calculate all the losses. Then all the losses will be send it to the optimizers. In that optimizers actually is responsible for doing the backward propagation, where it tries to minimize the loss. So for all the optimizers I have actually made a video in my deep neural basic playlist, so you can guys go and check out there. Okay, so let's discuss about vanishing gradient. So why it is called vanishing gradient? Actually it vanishes, or uh, the weight optimization or updation doesn't happen. So vanishing, okay, at the end of the video you can easily understand like why it is said that vanishing gradient problem. So gradient means actually the problem occurs in the gradient is nothing but the change of loss with respect to the weight. So this is nothing but the gradient, so problem occurs here. Like how it occurs, just let's see. So if you notice this particular two layers architecture, neural architecture, so you can see if we want to calculate the gradient. So if you go from the backward propagation, this particular output coming from this neuron, and this particular output actually dependent on this output, right? O1, and this particular output O1 actually dependent on the previous weights, because we are not getting any output from this particular layer. This is nothing but the input source. So whatever input actually we are getting, this actually multiplied with the weight, and with addition of some biases passes to the particular activation function, whatever activation function we have used in that particular hidden layer. So we have used sigmoid activation function for both hidden layer and the output layer here. So okay. As the basic thing that you want to remember is this particular output is dependent on this output, and this output is dependent on this particular weight. So if we are going to change this particular weight, so in the backward propagation we need to go through the all dependencies. Okay, so three dependencies is there most probably, and if we want to calculate the gradient of the particular weight, so we need to mm, this is the first layer for the backward propagation. So change of this, like what is the change of this particular output O to one with respect to this O change of O11. So yes, for chain rule we can write this derivative of O21 with respect to O11, and this particular O11 is dependent on this particular W11. This is nothing but the weight. Okay, so we can write derivative of O11 with respect to derivative of W11. So this is nothing but the simple chain rule. If you cancelize this two, this actually basically turns into the gradient. This is nothing but the loss. Okay, okay. So if you calculate this particular derivative for this two layer architecture, so in that particular two layers actually we have used derivative sigmoid activation function. So this is the graph of sigmoid function, as you can see. So if you construct the graph for any sigmoid function taking the z value as the input for any input for the sigmoid function, z is nothing but the input, right? The input, whatever input coming to this particular layer, In that particular layer we have sigmoid activation function. So what is the input coming? That is z. Z is nothing but the multiplicative summation of input and weight with some bias, right? So if we are going to construct uh, the graph, this nothing but the ranges from 0 to 1. This is nothing but the 1. So this is the origin 0. So all the values after after transforming from this activation function, that is sigmoid, actually it gets out as from 0 to 1 values. Okay, and if you try to take the derivative, so derivative of sigmoid function is nothing but this graph. So this graph actually basically ranges from 0 to 0.25. So the derivative of sigmoid activation function ranges from 0 to 0.25. It is practically proven also. So yes, let's come to calculate the gradient. So if you're gonna calculate the gradient, so as you can see, if you take this particular chain rule and try to multiply it, so this is nothing but the derivative of activation function with that is sigmoid, because in that particular layer we have used sigmoid activation function. In this particular layer also we have taken sigmoid activation function. So if you take the derivative and try to multiply it, so this for initial, if you going to the calculate backward propagation, so this is nothing but the first layer for this in initial layer for the backward propagation. So for this particular layer, if you try to go forward, the derivative will decrease, exponentially decrease, like whatever derivative value you are getting for this layer, actually it decreases the next layer. So slowly it will try to decrease. But initially it will be quite closer to the 0.25. Supposedly we are taking 0.20 for this layer, the derivative of this output with respect to the previous output. So supposedly we are taking 0.20, and this particular derivative of sigma activation function would be 0.04, 0.04. And if we are going to multiply this, so we will get very much very much small value. So which is nothing but is close to 0. So if we are going to apply that particular value in our weight optimization formula, this is nothing but the weight optimization formula, as we can see, as we have already known that. So if you going to put this particular small value to this weight optimization formula, so it's nothing but very small change, very small change will happen. So it actually initially supposedly were taken the 3.5. So this is nothing but 3.5 is the weight, and we have used all segment function in all layers, and this is the significant changes actually happens. So it's hardly changes any value. So 3.5, it used to be in the initial weight, but after calculating weight updation, it is giving 3.49. So it hardly changes any value, means the new weight is nearly equal to the old weight, nearly equal. So if you here actually I have taken only two layers, so we have got some two gradient to multiply. If we have some large number of layers, so this small value will go up to some 10 to the power minus 6 or 7. So it will be very small value, so it hardly changes any weight. So this particular gradient will come to nearly equal to 0. So it vanishes. So it is called as vanishing gradient. So the gradient actually vanishes, it comes to as 0. So that's why actually we don't use sigmoid for all the layers. If we use sigmoid for all the layers, we can get vanishing gradient problem. So for eradicating this vanishing gradient problem, we can use ReLU activation function as well. So this is all about vanishing gradient problem. So if you don't understand, and if you have any doubt, try to comment me out. I'll try to solve your queries in comment section. Thank you guys.